Hello, welcome. Welcome to part 1 of module 1. In this module, we're going to cover what is known as free body diagram, a concept from mechanics. And along the way, we're going to cover a few definitions that you already know about, such as mass, density, volume, etc. And we'll rapidly move into solving a simple problem based on the concept we cover. So our goal would be to quickly cover a particular concept and then solidify it by solving problems over the concept. So please feel free to go over a concept and try to solve a problem on your own before moving on to the next concept. Okay, so let's start with mass. So what is mass? Before we say what is mass, let's define what is called in thermodynamics a system. What is a system? Anything with a boundary. This line that we draw is called a boundary. It can be a physical boundary of a body or completely imaginary. But it's very easy to imagine something, a boundary that encloses a space. Whatever is inside is called a system, and whatever is outside is called the surroundings. So let's start with what is mass of the system. Mass, the symbol we use is called m, and the unit we use is called kg, and that's the System International SI unit. So whenever we cover a property, a quantity, such as mass, volume, force, pressure, etc., immediately the first task for you is to understand what symbol we use, what is the SI unit, and then have a concept of benchmark. What do I mean by that? A benchmark means so that you have something in front of you about a quantity. If somebody says length, or immediately you understand what 10 feet means, or say 3 meter means. Volume, you can pretty much, what's the volume of your room? Probably you can quickly guess. Mass, similarly, our benchmark for mass is going to be a typical football player, let's say, of mass of 100 kg. So what is mass? Basically, mass is the amount of matter inside the system, correct? So what is the minimum value of a mass? Of course, if there is nothing inside the system, the minimum value is going to be 0, and mass can be as high as infinity. Mass can never be negative. So these concepts you know already. I just want to harp on it so that you don't confuse mass with weight, which I'm going to cover next. But before that, a simple formula. We know mass of a system is given by density times volume, right? Where mass is in kg, density is kg per meter cube, and volume is meter cube. Everybody knows this formula. So what is the benchmark for density? Density of water, as you know, is about 1000 kg per meter cube. And another benchmark that I always encourage everyone to memorize is that of air, surrounding air that you see. It's not exactly 1, it's about 1 kg per meter cube. But it's good to know. So suppose you look at your bathtub and it's, you guess the volume there. Maybe the volume is about 1 meter cube. So the bathtub will have a mass of 1000 kg of water. Whereas your room probably is about 100 meter cube. It will have about 100 kg of water, of air. So this is the purpose of benchmark, and we are going to have benchmark for every quantity that we come across, every property that we cover. Okay, let's go into force. Again, these are all familiar concepts. I'm just going to quickly brush over them. The force, the symbol is F, and in mechanics we use the unit Newton. Unfortunately, Newton is very small quantity. So in thermo, we are going to use kilonewton, 1,000 Newton. That will be our preferred unit. So what is force? Very simply, force is, the sense of push and pull. Just that. So let's start with a very, very familiar force so that we can benchmark it. We know we know what is gravitational attraction. Suppose there's a little mass m. This is Earth of mass capital M. Obviously, they are not to scale. And suppose it's at a height z from the surface. I know you are used to saying height is h, but in thermodynamics, h is reserved for something else, a property called enthalpy. So we are not going to use h for that. So z is the height of the small mass m. And let's say that from the center of the Earth, the radius is capital R. So Newton's law of gravitation will say the force of gravity is what? Is gravitational constant times the two masses divided by the distance that separates them. A square of that, inverse square law of gravity. So this is the force with which F is the force with which Earth pulls a mass, and that's called the weight, and we give it a special symbol W. We all know W equals mg, where g is small g, but let's see the origin of that. So this is the fundamental formula. The weight of a body is given by this particular formula. Now, we all understand R is way, way bigger than Z, right? For a given height. Suppose Earth has a big radius compared to most of the systems that you can see on Earth. So therefore, weight can be approximated as g mm over capital R square. Obviously, we notice that the weight is going to decrease if z becomes really, really high. Suppose you go on the top of a very big mountain, yes, then the force will decrease. So this constant, so suppose we express W as m times R plus Z square, then this part is what we can substitute by a new symbol. So that's our G that we are familiar with in engineering. Physicists probably are more familiar with or as familiar with the gravitational constant. But we don't have to memorize what is the value of gravitational constant. For us, small g, which is composed of the gravitational constant, the mass of Earth, the radius, and the height of your object, of your system, is a simpler concept. So you can see that small g decreases as capital Z increases. As Z increases. So the typical value of G is about 9.81 meter per second square. That's the value at the sea level. Of course, as Z goes up, as Z increases, you can see G will go down as Z goes up. So we are going to approximate G with about 10 meter per second square when you have to quickly solve a problem or quickly come up with a benchmark. It's a good idea to always remember the value of small g. Now you may ask, why in the world this force unit suddenly became acceleration unit? Why do you call small g acceleration due to gravity? After all, it comes from the Newton's gravitational formula, and this constant, it happens to have a unit of meter per second square, which we know is the unit of acceleration. We also know that most of us call small g as acceleration due to gravity. And the reason for that, to understand the reason for that, we have to understand what is known as a free body diagram. And that really is the emphasis of this lecture today. So what we just learned is that if I have a small mass m, then it's pulled by earth with a force mg. And by the way, the unit of, if m is in kg and g is in meter per second square, the unit of weight is Newton. But we know in thermodynamics we want to use always kilonewton. So in kilonewton, weight will be mg divided by 1000. So this will be our reformulated formula for weight of a body of mass m. So mass is the amount of matter and weight is the force with which earth is pulling it. And that should be our bridge between force versus mass. So let's understand why small g is called acceleration due to gravity. Suppose I'm holding this body in my hand. So that means earth is pulling it with a force mg, or mg over 1000. And if I'm holding it on my hand, that means what? It must be not accelerating, right? It's in equilibrium, force equilibrium. So the only way that can happen is that if I am pushing it with a force which is exactly equal to mg. So in other words, when a body doesn't accelerate, it has to be in force equilibrium. The upward force and downward force must be equal if the only force is because of the gravitational force. So if I'm holding something, we know earth is still pulling into the mg. However, suppose I don't hold it, I just move my hand away. Then what will happen? Then we know that with this force earth is pulling it, and according to Newton's second law of motion, so Newton's second law will tell us what? That force equal mass times acceleration. What is our force? Is the weight. Mass times acceleration. But we already proved that weight is nothing but mg, which is mass times acceleration. By the way, these formulas are all in Newton for our discussion here. So we can see that mass get cancelled and therefore g equals a. In other words, if I let a body go on earth, because of gravitational force, it will accelerate with an acceleration equals g. That's why this is called acceleration due to gravity. So I hope you appreciate the connection between Newton's law of gravitation and Newton's second law of motion. When you connect the two together, we come up with acceleration due to gravity. Well, so it seems like the free body diagram is an important concept because it allows us to understand how force is balanced on a system. So with that in the background, I want to introduce another property now, which is pressure. The symbol we are going to use is small p, and the unit of pressure is kilopascal or kilonewton per meter square. Well, what is pressure? Pressure is basically force per unit area, force divided by area. So P is force per unit area, as simple as that. So the unit of pressure will be what? Force, if force is in kilonewton, area is in meter square, and that's called kilopascal. As simple as that. So let's understand what is pressure and force together. So let's go back to our benchmark for mass. So suppose we go back to our football player who has a mass of 100 kg. So what will be his weight? weight will be mg divided by 1000. Would you agree? Which is 100 times approximately g is about 10 by 1000. So that becomes 1 kilonewton. So for force, we have a nice benchmark. If we have a football player who is a typical weight of 100 kg, give or take, then his weight is 1 kilonewton. So very easy to understand force now, correct? By the way, think of an apple. What do you think is the weight of an apple? It's a newton. And I'm not, and no pun intended here. So a football player is our benchmark, who has a weight of 1 kilonewton. So with that in background, let's try to understand pressure and have a benchmark for that. First of all, what is pressure? Suppose I have a tank of gas. So you can understand that gas molecules are going to go bounce off the wall, and when it bounces off the wall, it kind of, its momentum get changed, right? Just like a billiard ball. If you hit the wall with a ball and it bounces back, you are imparting momentum into the wall. And you can show, you must know from mechanics, that means the wall must be imparting a force on this body. So if there is millions and billions of collisions like that with the wall must experience a force. And that force per unit area is our pressure. It is so fundamental. So a gas at a given temperature, and a given temperature will and mass will exert a certain amount of force on the wall. It doesn't matter if you take this tank to the space station or to another planet, as long as the temperature inside this doesn't change, the force experienced at the wall will be exactly the same. And the area is also not going to change, so the pressure inside is going to remain the same. That should not be confused with, suppose I have a tank of water. We all know that as you go down, pressure increases. And that's because of hydrostatic pressure, because gravity is present here. So this is what is known as thermodynamic pressure, that in this case the pressure doesn't change whether it's on Earth or in another or space or anywhere. Whereas here the variation is just because of gravity. As you go down in a swimming pool, you'll find the pressure is increasing. So this hydrostatic pressure variation in thermodynamics most of the time we'll neglect. However, you got to understand that if you take a little small system here, inside this system you can think like the pressure inside is behaving like a thermodynamic pressure. We'll come back to that when we discuss equilibrium later on. So for the time being, if you just assume or just understand pressure as force per unit area, which is property of the system and doesn't depend on anything else, think like that, and that will suffice. So with that in the background, let's quickly go and try to set up a problem and see if we can make sense out of that. Suppose I say here is a piston cylinder device. Basically, we'll do this so many times, we'll get used to this. There is no friction. We'll assume there is no friction between the piston and the cylinder, so that the piston is free to move. And suppose we put a weight of 100 kg, a mass of 100 kg on this piston. So the benchmark, by the way, atmosphere outside has a pressure, and we'll typically call it P0. And a benchmark for pressure could be P0, which is about 100 kPa. Well, that's a lot of force per unit area. Think about it. 1 kPa is the weight of one football player. So what is kPa? Recall, kPa means kilonewton per meter square, right? So if you think if I have a piston which is about a meter square, a meter by meter, A meter is about 3 feet, so everybody a yard. So you can visualize what is a meter square. So atmosphere has a pressure of 100 kPa. Just try to understand what that means. That means if suppose I have a plate of 1 meter square area, then the atmosphere will be pushing it down by a force of P0 times A, which is 100 kilonewton. And it is same as if there are 100 football players standing on the plate. Think about it. That's equivalent. Whereas we can say, wait a minute, I can hold the plate without any problem, even though there is 100 football player on top. That's because there is 100 kPa or 100 kilonewton of force from the bottom when there is a plate. So all you have to do to hold a plate is to support the weight of the plate, because the atmospheric force from the top and bottom, they cancel out. So now go to this problem. What is going on here? There is the gas inside has a pressure of, let's say, Pi. So the question could be, find the pressure Pi inside. To do so, we can do a free body diagram of the piston. So that's our clue here. So we draw the piston and we recognize that atmosphere will push it down with a force of P0A. The gas inside will try to push it up with a force of Pi times A, and the weight that is on top puts an additional force of mg over 1000. Can you see that? So the force balance, upward force and downward force, must be equal if the piston is in equilibrium. That is, there is no net force, there is no acceleration of the piston. In that case, if we write all the upward force, the equation of balance, the force balance becomes upward force equals downward force. So these are all in kilonewton. So therefore, Pi can be found to be equals P0 plus mg over 1000 times area. Let's make up a problem. It's 100 kg. Let's just assume it's 0.5 meter square. In that case, or let's assume it to be 1 meter square. So if the piston has the area of 1 meter square, I'm making up a very simple problem. Then the inside pressure must be what? 100 plus, remember, mass is 100 kg, and g we are approximating 10, so that I don't need a calculator. And this is 1000 and 1. So you can see this is 101 kPa. So to support the weight of 100 kg, all I need is a force inside, a pressure inside of 101 kPa. So this is the use of free body diagram. To understand free body diagram even more thoroughly, you can go to thermofluids.net and log in and go to the animations module. And in chapter 0, which is you can see different sections, and the free body is the first section. You can just move through and you will see it explains the concept of weight, the concept of free body diagram for various systems, and specifically I'd request that you go over this particular example that we just solved, and it explains how to draw the free body diagram step by step, and kind of also the what if scenario, that you can click what happens if the gas is heated. You can see that the free body diagram balance doesn't change. By the way, also you can pause the animation anytime by clicking the stop button here and go back and forth, moving the pointer, the slider to any desired point. So it gives you a nice tool at your hand, and all you need is Firefox with a Flash animation plugin, Flash plugin, Adobe Flash plugin. Okay, so now it's time to go for you to and solve the problem that accompanies this particular module.